Hello children, in the chapter circles, in the previous class, we have studied about circle and the various terms related to it, like center, radius, chord, diameter, arc, segment and sector, etc. In this class, we will discuss different situations when we are given a line and a circle. Now, if a circle is given, then say O is the center. Let us draw a line segment that intersects the circle at two distinct points. We say secant. A line that intersects the circle at two distinct points. We say what? Secant. Like that, we can draw any number of secants. While we doing so, just we observe a line that touches the circle at one and only one point. Such a line, we say tangent. Such a line we say what? Tangent. I hope now it is clear. See here, a line that intersects a circle at two distinct points. We say secant. A line that touches the circle, a line that meets the circle at what? Only one point. We say tangent. Okay, children. Then that point we say point of contact. Point of contact. Today's our lesson focuses on these 2 points only. Which are the 2 points? One is this tangent and the point of contact. Okay, children. Now, secant. Let us try to understand these terms with the help of a simple figure. Okay, what is secant? Is a line segment. Look at children here. A line segment intersecting, or just a line intersecting a circle in 2 points. Hence here, this one, A, B is a secant. Why? Because this intersects the circle at 2 points. Such a line we say secant. Next, tangent. Already we discussed. A line that touches the circle at one and only one point. That we say tangent. A tangent to a circle is a line that intersects. Here intersection means need not be 2 points, even at 1 point. Okay, intersects, or okay, let us say as what? Touches the circle at only 1 point. Which is that point here? P. What do you call that point? Point of contact. So what is point of contact? It is nothing but the common point between the circle and tangent. The common point. Now we are very clear. Tangent is a line that touches the circle at one and only one point. Therefore, that point which is common to the circle and the tangent is a point of contact. Very important point, that one. A tangent to a circle is a line that intersects or touches the circle at only one point. This common point is called what? Point of contact. Because here the complete scenario, all the properties of the tangents, based on this point of contact. That's why know it clearly. Next, length of tangent. Generally, to a circle, if a tangent is drawn, it can be extended to any extent. But here, when we say length, we have to be very careful while defining the length of the tangent. Look at here. Length of tangent. The length of the segment of the tangent. What is that segment? Here, by definition, we know a tangent is a straight line. Means it can be extended to any length. Now, what should be the length of the segment of the tangent means? We should know if we are given some point from this point, say Q, to this point of contact, this we say the length of the tangent. See here, the length of the segment of the tangent between the given point and the point of contact. Between the given point and the point of contact is called length of tangent. Hence, children, with the help of these particular terms, secant, tangent, point of contact and length of tangent, we have two theorems. Now we shall try to prove those two theorems. Theorem 1. The tangent at any point of a circle is perpendicular to the radius through the point of contact. As we know, in a theorem, there are two parts. The first one is given. The next part we have to prove. Here what is given? The tangent at any point of a circle. Hence, consider a circle with center O. Tangent. Tangent, by definition, we know a line just that touches the circle at one and only one point. Say P is the point of contact and A, B. These two denote the tangent. Okay, now the tangent at any point of a circle, here P is that point, any circle, is perpendicular to the radius. So we know radius is a line segment that joins center to any point. Now therefore, children, what we have to prove here? We have to prove that radius is perpendicular to the tangent. Okay. Now first we shall take the data. What is given? Here AB is a tangent. The tangent is given. AB is a tangent at P to a circle. With center O. Okay, children. So this much is given. A tangent, look at that, tangent at any point of a circle. Here this circle is having what? The center O. Okay, so therefore the data can be written like this. AB is a tangent at P to a circle with center O. Next, what we have to prove? That radius is perpendicular to the tangent or tangent is perpendicular to the radius. Therefore, that is the one we have to prove. What we have to prove? OP perpendicular to the tangent. That means tangent perpendicular to the radius drawn at the point of contact. Here we need some construction to have that logical steps. What is that? Let us mark any point Q. This Q, what is the speciality of Q? Q is a point other than P on AB. Q is a point. Therefore, construction. Mark a point Q on AB other than P, because P is a common point. Even it is on the circle as well as on AB. Here we have to select Q in such a way that it should be other than P. Then join OQ. Join OQ. Join OQ. And let us mark this point B R. Next we shall take proof. From the figure OP equal to OR. Why these two are equal? You know, because these two are what? Radii of the same circle. Radius singular, radii plural form. OP equal to OR. Call this as equation 1. And now OQ equal to OR plus QR. Correct? OQ equal to what? OR plus QR. What is the reason? Reason is nothing but common sense. That's all. Therefore, here OQ is nothing but the sum of OR plus OQ. That means here OQ is equal. OQ is equal to OR plus QR. If I take OQ and OR leaving this QR, then what could be the relation between OQ and OR? Look at once again. OQ equal to OR plus QR. Okay. If I take OQ and OR, now just you relate these two. What should be the relation of all the possible relations? Either they have to be equal, or it should be lesser, or it should be greater. Okay. So now therefore children, OQ equal to OR plus QR. When you take only OR leaving QR means just simple common sense. OQ must be what? Greater than OR. Understood? Okay. Now therefore, OQ from 1. What is OR? OR is nothing but OP. OP. Okay, children. Now therefore here, just look at that simple relation, but that speaks a lot. What is that? OQ is greater than OP. This means what? In the construction we have taken what? A point Q on AB other than P means Q represents all the points except P. Therefore, this means OQ is greater than whichever the point you take, any point here, this point, okay, or you take one more point, all this, since it is any point means here, this means that what? OP is the shortest side drawn from O to AB. Understood? Therefore, when a line, that means from a given external point to a given line, many lines can be drawn. Among them, infinite number of lines can be drawn. And here, what is the speciality of the shortest means? Shortest will be the perpendicular. I hope you understood. Once again, listen. From an external point to a given line, infinite number of lines can be drawn. Of all the straight lines that can be drawn from an external point, the shortest will be the perpendicular. That factor we know. Now therefore, this OQ greater than OP, This tells us what OP is the shortest. OP is the shortest. OP is the shortest. Here I am writing shortest line segment. Line in a shortest line drawn from O. Drawn from O to AB. Drawn from O to AB. OP is the shortest line drawn from O to AB. This implies OP perpendicular to AB. OP perpendicular to AB. With respect to here the given theorem, what is OP? It is the radius. What is AB? Tangent. Thus, tangent is perpendicular to the radius drawn at the point of contact. Okay. Second theorem. The lengths of tangents drawn from an external point to a circle are equal. Hence, here also we have two parts. First is given. The next half of the statement is the one we have to prove. The lengths of tangents drawn from an external point to a circle. Consider a circle with the center O. Say P is an external point. From an external point, how many tangents can be drawn? At the most, only two tangents can be drawn. Say A, point of contact, B, point of contact. Now what the theorem says? The lengths of tangents, we know by definition the length of tangent. It is the distance between the given point on the tangent. Tangent can be extended to any length. When we are very particular about the length, we should take that length from the given point to the point of contact. So therefore, the lengths of tangents here, PA and PB, those two we have to prove as what? Equal. Okay, therefore the lengths of tangent. Then what is the data? PA and PB are the two tangents. Drawn from P to a circle, symbol of circle, a circle with center O. So this is what the given, or we say data. Next, what we have to prove? The point to be proved is this: the lengths of tangents drawn from an external point to a circle are equal. Hence, children, what we have to prove? We have to prove PA is equal to PB. PA equal to PB. Construction. Let us join OA, OB and OP just to distinguish the construction from the given. Better, let us draw by dotted line. Join OA, what is that? Radius, OB, radius, and OP. What is OP? It is the line joining the center and the external point. Okay. Now, what we have to prove? PA equal to PB. In our secondary schools, high schools, whenever we have to prove two line segments as equal, first you identify the corresponding respective triangles to which those two line segments belong. These two line segments belong. Here PA now belongs to a triangle AOP. PB belongs to a triangle OBP. Hence, in order to prove them as equal, if we prove these two triangles as congruent, that's enough. Okay, you know the meaning of congruent, equal in all aspects. Okay, children. Now, therefore, we have to prove these two triangles as what? Congruent. Once the triangles become congruent, then CPCT, corresponding parts of congruent triangles, by applying that property, we can get the result, required result P and PB as what? Equal. Okay. Proof from the figure. From the figure, when we collect some important points from the figure, then it's better. Let us start like this. From the figure, OA perpendicular to AP. OA perpendicular to AP. OB perpendicular to BP. In geometry, each and especially while we proving the theorems or when we take riders, for each and everything we have to reason out on what basis this comes. That we have to say. What is OA, children? OA is radius. What is AP? Tangent. There I have written as perpendicular. How? Just now we have proved theorem 1. Therefore, according to that, here we need not write as theorem 1. Instead, let us write the feature property itself. What is the property? Property is this. Radius is perpendicular to what? Tangent. Radius perpendicular to tangent. So, thus we shall write here radius perpendicular to tangent. So, this is the reason. Okay, therefore, in both the cases, radius perpendicular to tangent, radius perpendicular to tangent. Okay, now, therefore, this implies, we should write therefore, angle OAP equal to OBP equal to what? 90 degree, because perpendicular, therefore naturally it will be what? 90 degree. Now we shall take the required triangles. In triangle OAP and triangle OBP. Why here I started with triangle OAP? Because here the unknown PA is in the left hand side. Therefore, it is in practice we have start with that triangle only in the beginning. Therefore, PA, since PA belongs to OAP, better let us start with that triangle. In triangle OAP and OBP, okay, compare them. Angle OAP equal to angle OBP. Just now we have proved both are equal to 90 degree. Here we need not to once again give reason. Just now we have proved no. Just we are accepting the result. And what is this factor, children? It is right angle. The factor R. Okay. You know, to prove any two triangles as congruent, we need at least what? 3 factors. Maybe etc. sides or angles and so on. Just we go on comparing. Okay, we got now triangle. Therefore now OAP, OBP equal to 90 degree. This tells us what? These two are right triangles. Okay. In right triangles, we got R. Next, in this right triangle and in this right triangle, in both are having what? The hypotenuse as common one. Therefore, which is the hypotenuse for this? OP. Hypotenuse for this triangle? OP. Hence, OP is common. OP is common. What is this? Nothing but the factor H. Okay. We need just one more sign. In case of two right triangle, in order to prove them as congruent, we need what? RHS postulate. We got R, H. We need just S factor. What now? What about Y and OB? Are they equal? Yes, they are equal. Y radii. Hence here and OA equal to OB. What is the reason? Radii. What are these? Nothing but yes. Thus, for triangle OAP congruent to triangle OBP. According to which postulate? RHS. Right angle, hypotenuse and side. Okay, children. So thus these two triangles are now what? Congruent. Once the triangles become congruent, now without any hesitation, we can say what? All the remaining elements are also equal. Here, now, which is that unknown factor? P and PB. Now, therefore, we can say what? PA equal to PB. Therefore, PA equal to PB. What is the reason? Reason is this: CP, Do you know that? Corresponding parts of congruent triangles. Okay, children. Now, therefore, here, what is P and PB with respect to these two triangles? These are nothing, just sides. But with respect to the given data, P and PB are what? Tangents. Thus, the lengths of tangents drawn from external point to a circle are equal. Understood? Okay, children, now we have proved two theorems. In the next class, we will take numericals and riders based on these two theorems. Thank you, children.